This is the North Yungas Road, a ribbon of stone carved into the spine of the Andes. A route where the margin for error is measured in inches, not feet. How did engineers and laborers transform this vertical challenge into a transport corridor?
The geography itself was the first, and perhaps the greatest, obstacle to overcome.
Water and gravity are the constants here, forever threatening the stability of the route. But why was a road built here, in one of the world's most unforgiving terrains? To understand the road, we must go back to the early 20th century. Bolivia needed a connection to bridge the isolation between the mountains and the tropical forests. The route was defined by the necessity of commerce and the sheer limits of mountain engineering. There were no easy paths, only the choices forced by the steep, unstable geology. Initial surveys had to account for every meter of elevation change and rock stability. Human labor was the primary engine, shaping the earth one strike at a time. Each section required complex calculations regarding the natural repose of the mountain soil. The choice of route was a gamble between distance and physical feasibility. This environment is characterized by intense moisture and sudden geological change. The climate promotes rapid erosion, constantly challenging any structure placed upon the slope. Water management was the most critical engineering task for this mountain corridor. Daily rainfall frequently saturates the earth, triggering minor, constant geological shifts. The soil here is not solid. It is a delicate balance of rock and loose, hydrated earth. Elevation dictates the vegetation and the weather, creating distinct operational zones. Engineers had to work within these constraints, carving into the slope rather than bridging it. Geography provided the path, but it dictated the limits of every structural intervention. Route selection was a brutal exercise in geometry and risk management. Each bend was calculated to maintain a constant, manageable gradient on the vertical terrain. The route was defined by the necessity of commerce and the sheer limits of mountain engineering. Every centimeter of width had to be hacked from the solid mountain wall. Where the mountain resisted hand tools, controlled blasting opened the path forward. Blasting was used sparingly, limited by the fear of causing massive rock falls. Construction progressed slowly, fighting the mountain to gain each meter of passage. By following the terrain, the engineers created a path that hugged the mountain's contours. The construction crews worked with limited machinery, relying on manual labor. The preparation of the roadbed was as important as the excavation itself. These men worked on precarious scaffolds, often suspended over the deep jungle canyons. Every bit of removed earth had to be managed to prevent landslides below the worksite. Tools were kept sharp and operational, as the mountain's resistance was relentless. Sections were completed sequentially, moving from the easier gradients into the cliffs. Retaining walls were hand-built, reinforcing the soft, unstable mountainside. These structures were essential, providing a foundation for the road where nature provided none. Progress was measured in meters, but it was an achievement of immense scale. A route that was once a faint, dangerous trail now began to function as a road.
The road surface was initially just leveled dirt and gravel, prone to mud. Drainage pipes and simple channels were installed to redirect runoff away from the roadbed.
Redirecting water was the key to keeping the road functional during the rainy season. As the road matured, it began to support the transport of goods and people. Operators quickly learned the hazards of the narrow width and the steep precipices. Passing other vehicles required nerves of steel and perfect coordination of space. Redirecting water was the key to keeping the road functional during the rainy season. Each completed section increased the utility of the road, but also its operational risks. Maintenance crews were permanently stationed, as the mountain constantly sought to reclaim the road. The road was no longer just a path. It was a complex piece of engineering infrastructure. Then, the rains would begin, turning engineering challenges into survival obstacles. Excess water quickly undermined the compacted surface, threatening the road's integrity.
When systems were overwhelmed, water had nowhere to go but across the path.
Instability in the slope could trigger immediate, localized slides that blocked the path.
Clearing these obstructions was a constant, dangerous reality for anyone maintaining the road.
Structural erosion often started invisibly, deep beneath the surface material. The cliff edge was always a risk, as the mountain face itself proved to be fragile. Drivers had to read the road's condition, recognizing the danger hidden in the mud. Nature gave, and nature took, with little warning or compromise. But the road persisted, a testament to the engineering necessity of the route. Operating the road demanded total awareness of vehicle position and slope conditions. With no physical barriers, the only safety measures were experience and caution.
Turning geometry was tight, forcing oversized vehicles to perform complex maneuvers.
Communication between drivers became a necessity, often using signals or honks. Visibility was often limited by thick mountain fog, turning simple turns into blind gambles. When the mist closed in, speed had to be reduced to almost a walking pace. Drivers understood that the road belonged to everyone, and cooperation saved lives. Operations continued around the clock, with the road functioning as a vital arterial link.
The road never slept, because the cargo it carried could not afford to wait.
Each dawn saw the cycle of passage begin again, testing the engineering and the human element. The road's reputation as the world's most dangerous route grew with every harrowing crossing. But behind the sensational titles lie the real histories of those who worked and traveled here. The danger was real, yet it was also often magnified by the isolation of the terrain. Was it a death trap, or was it a necessary triumph of human engineering against the odds?
Organized logistics and careful driving became the engineering answer to the inherent environmental risk.
Rigorous vehicle maintenance was the silent partner in the road's operational safety. The reality was complex, shaped by history, geography, and the simple need for transport. It wasn't just a road. It was a permanent debate between human intent and the Earth's response. Eventually, the road's primary transport role was replaced by more efficient, modern alternatives.
The route transitioned, becoming a destination for adventure travel and a historic corridor.
While traffic is lower, the road remains a testament to the era that built it. For those living in the region, the road remains a crucial thread in their daily connection.
This contrast reminds us how engineering must evolve alongside our changing needs.
It is a bridge between the past, the present, and the engineering potential of the future. A living monument to the human effort to overcome the limits of geography. The North Yungas Road reveals that engineering is not just about tools, but about understanding the Earth. By looking at this road, we see the true, immense scale of our interaction with nature. Every curve here teaches us that we can adapt to any constraint if we understand the physics. Faced with this same vertical terrain, would you have followed this route or searched for another way? The answers to these engineering questions are still being written as we look to build in even more extreme environments across our world.